really a state-of-the-art of satellite data, optical and radar, understanding all the properties of those two different types of satellites, because they're really different, and then they will have very different consequences on the use on the different application. For example, benthic monitoring. And then tomorrow morning, we'll have a shorter session where we will see how exactly on specific use case, on existing, ongoing, or finished project, how those principles apply and what are the consequences in terms of science, in terms of accuracy, and in terms of validation. So if you're all ready, we will begin. I should be able to see if you raise your hand, but in any case, I will try. Yes, Carla. I will stop sometimes, two times, to see if you have any question relative to the topic that we just had. So you also have some dedicated time to ask a question before the end of the whole presentation, because it's going to be a one. Yes, Patrick? Okay. All right. So if you're all ready, let's start. So as I said, we will see the different most used satellites for Earth observation, the optical one and the radar or SAR. You will see I will use a lot of SAR data to speak of the radar data. So those two type of sensors are the most used for the Earth observation application. Why? Because, well, we're going to go through the presentation today to see why those properties, why those signals are really helpful to scientists to visualize, monitor, and analyze different Earth phenomena, but also human activities. So for those sensors, there is, even if they are really different, there is three components that are always necessary to understand, and they are valid for all those two satellites. It's the temporal resolution. So the temporal resolution is how many days I have between two images of the same place. We have then the spectral resolution. Spectral resolution is how many different spectral information I can have, what is the wide spectrum information I can get. And the spatial resolution is linked with the features I can see on the ground. We can also use the word pixel size for the spatial resolution. So let's kick off with the optical satellite data. So the satellite data, how the data are acquired. So for the satellite data, if I take the example of Sentinel-2, and also Sentinel-3, we have a constellation of satellites, meaning multiple satellites are orbiting the Earth, which allow us then to have a higher accuracy of the temporal resolution. They are working together, and when two satellites of the same mission, for example, Sentinel-2A, B, or C, are working together, we're calling that a constellation. For a constellation to work, it's really essential that we can't make the difference between the two satellites. If I show you a picture of Sentinel-2A, it's exactly the same as a picture of Sentinel-2B. Oh. And that's those two satellites working together allow us to have a map of the temporal resolution. So here the example of Sentinel-2 data. So the map has been done by ESA, which is the operator of the mission. And we can see that for most latitudes, we have a repetition of 5 days. So I raise here your attention because there is some studies and you're going to find some paper that is selling artificially how to reduce that temporal resolution and how to create data between the real acquisition. We have to be very careful because that is creating data from non-existent source. So this temporal resolution is the smallest you can have as the most higher accuracy in terms of information. So the acquisition mode, and more essentially the sensor type, is also helping defining the spectral resolution. So the spectral resolution is how many sections of the spectrum we can have access to. So how the satellites, optical satellites, is working? Well, you have the sun, sorry, you have the sun that is illuminating the Earth, and all the sun signal, the reflectances, is being bounced back to the satellite, and when the satellite passes over, we can take a picture. So it's really actually working just by the reflectance of Earth's features that the satellite can capture. So if you have a cloud, for example, it's going to block the signal. So it's basically working like a camera that you and I can have. It's really just taking a picture of the Earth, and so we can see optical features. So how does it work? Because if I take a picture with my camera, I have all the colors that are automatically visible. So satellite data we can reproduce what we call an RGB view. So exactly a human vision colors. But the satellite data doesn't take that picture. This is a reconstruction. How the satellite is working is taking pictures on specific wavelengths. So here is the image that is being acquired in the blue, and each pixel will have the reflectance value, the intensity of the reflectance for the blue channel. So taking all those different bands together, blue, green, red, infrared, we can then build an RGB view using all the independent picture. You can see that on our RGB view of the forest, so this is a picture of the Amazon forest, we have a lot of green because the forest have very, very high reflectance in green. As you can see here on the green picture, the forest in the green wavelengths is where we have the highest reflectance signal. Of course, infrared is the most important for the forest because that will be the highest reflectance for forest, and actually for forest monitoring, the infrared band is the one that is most used. You all know NDVI, for example, which is a combination of infrared. So back to Sentinel-2, for example, ESA optical satellite. Sentinel-2 has 12 bands, actually 13, because we have two band 8. We have 8A and 8B in the infrared system. So as you can see, the different bands are at different space, at different location of the spectrum. So the visible domain is really right here. So we just have a few bands in the visible domain. We have RGB and coastal. But most of information from Sentinel-2 are coming from the near domain and the SWIR, the far infrared domain. And this is called the spectral resolution. Each band, as you can see, is defined by a center wavelength and also a bandwidth. Because it's really important to know, because the only information I have on my Sentinel-2 band picture is the intensity of the reflectance. But I need to know this intensity in which portion of the electromagnetic spectrum. So having a large, like band 12 bandwidth, I don't know. I mean, there is a lot of wavelengths that are included in that band 12 reflectance information. But other bands like 5, 6, 7, 8, 9 are really, really, really narrow, which allow a very high accuracy monitoring and analysis. So that is for the spectral resolution. The last point we had for optical data was the spatial resolution, the size of the different pixels. So here I have different images. If I just look at them like that, we can't really see any differences. But they're all coming from different sensors. Worldview 3, which had a pixel resolution of 2 meters. Sentinel-2, our friend from the ESA Copernicus mission, at 10 meters. Landsat, which is the grandfather of Sentinel-2 from NASA, 15. And Landsat 5, the old one, 30 meters. And when we zoom, what does that mean to have this resolution? We can see different information on the ground. So In World View 3 at 2 meters, we can even see the car of the parking lot. Sentinel-2, we can see that here there is something, we might have a parking lot. Here, it's really difficult to make the difference between the houses. Here we know we have a pool, and Landsat 5, well, you're gonna have to be really specific and have a lot of context to understand what this picture represents. The spatial resolution, they all have different impact of your analysis. A lot of people think higher the resolution, so smaller the detail I can see, the better. Not always, because what spatial resolution mean? It means generalization. So here I've created a little picture of a forest with some bushes. So how the satellite, when it's going to pass over, is going to summarize the information to create pixels. So it's going to be about the size of the detail we can see. So first we have a grid, as you can see, and then from that grid, I'm going to summarize the information I have. So dark green will be the forest and light green will be the bushes. But as you see, my tree here is not being representative there. And I have some bushes in the forest that are not visible on my regeneralization of my satellite image. So you have to ask yourself, what is the level of generalization you want? Sometimes Sentinel-2 at 2 meters is really a good generalization type, especially if you do time series. Let's take the example of Spain, for example. Here we have a nice beach that during summer times, as you can see, a lot of tourists with umbrellas, and during the winter, nothing. You can also have some little restaurants that are just here during the summertime. If I'm taking a very high resolution picture like this one, trying to understand, for example, the limit, the boundary between the land and sea. This area at this resolution has so many variabilities. I mean, the satellite image can see so different things moving around that my analysis will be really, really noisy because of all those things that changes through times that are not interesting for my study. So the spatial resolution, the generalization level that you need to be decided according to your mission and to what you want to do. If you are studying the installation and the beach width of where the tourists are during the summer, yes, you need that kind of resolution. If you're trying to monitor larger phenomena, those tourists here during the summer times are just going to bring noise to your processes. So spatial resolution is a bigger question than just I take the smaller pixel size possible, because the generalization methodology could really impact your study. Before we go to the satellite data limitation, do you have any question about the three core principles: temporal resolution, spatial resolution, and spectral resolution? Is there any question? Okay, everything seems to be good. So let's continue on the limitation of the optical satellite data. So we saw that the satellite data is just passing over a scene and taking a picture, capturing the sun reflectance on the ground, which means that when we have a cloud, what we see, because the cloud will be between the Earth and the satellites. So what we see is actually the cloud, the sun reflectance of the cloud directly back to the satellite. So that is really difficult because, well, the cloud coverage around the Earth is not uniform. You have some areas that have way more cloudy season than others. And when you're trying to do a temporal analysis, for example, a seasonal analysis, a yearly analysis, this clouds, because you're not going to have the same number of cloudy image every year, is really going to be disruptive to your sampling resolution. You're not going to always have the same number of images available. You're not going to have the same number of images available on different locations on the Earth. And you never know when they're going to be. Sometimes you're going to have an over-representation of the season. And sometimes you're going to have too many images on one season, and that's going to bring a bias. So cloud coverage is really something to take into account, especially when you do temporal analysis, like we do, for example, in the Benthic Habitat Monitoring, to be sure that you don't over-represent, for example, summertime over wintertime. Another limitation is the spatial accuracy. I often take the example of bicycle to explain the spatial accuracy. If I take my bicycle to go to work, I'm always gonna take the same way. I'm always gonna use the same route. But will my tire track exactly be at the same position? No. And this is what's going on with, for example, Sentinel-2 data. The satellite is always passing over the same scene, but not exactly at the exact same track position. And we can observe with Sentinel-2 a shift, for example, up to 12 meters. So 12 meters was before 2024. ESA is actually proposing and testing a new algorithm that is now being implemented in the new data to reduce that spatial shift. But here we have a ground, and you can see that this location is exactly the same on my picture, but it's not the same identification on my ground space. So spatial accuracy is a limitation to be aware of, but a lot of co-registration processes are really accurate and can be really helpful to make the correction. And actually for the habitat monitoring, we are using co-registration to correct that shift. Because if you don't correct it, how can you be sure that what the change that you see, is it a real change in phenomenon, or is it just because your image is not at the same place? Limitation for optical satellites. Any question before we switch to radar data? No question? All right, so let's switch to radar data. So optical data was the, let's say, the most direct type of information. Yes? Sonia, you have a question? Hello? If you have a question, you can... Yeah.
We cannot hear you, Sonia. Sorry. Could you write it in the chat, please?
Okay. I don't know if the question is in time.
It's here. Can you see that? Or I can read. I can read it. She wrote, I want to ask about the trade-off between spatial and temporal resolution.
Ah, yes. Yes, of course. So when you have, I'm gonna just reuse, yes, this one. So there is no direct connection between spatial resolution and temporal resolution. It's not because you have a high spatial resolution that you're going to have a low spatial resolution. For example, Landsat 5, 30 meters, revisit time, 10 days, even 16, depending on the latitude. Sentinel-2, 10 meters, 5 days. So there is no direct link between the two. Worldview 3, commercial data. You have to pay for the data. Sometimes you can order the mission, and some other times you will have access to the archive. Now, for an analysis, when you have a study to make, what do you rather like to choose? Higher temporal resolution or higher spatial resolution? That depends on your analysis. If you're doing a temporal analysis of, let's say, the Amazonian forest, you know that yearly you will have deforestation, but the Amazonian forest is so wide and so big, and we know that the deforestation patch are really big. You don't need that level of accuracy. You can even use 15 meters because you know that the patches are going to be wide. Now, if you want to do a temporal analysis of as I said, for example, the tourist frequentation of a beach, you're going to need to be able to see the tourists. But you're gonna have, and you want to have an average through the summer. So one image per year in summertime is not going to be enough, because how do you know that this is the most representative day of the summer in terms of tourist frequentation? So you're going to have to need, for example, 1 or 2 images per month to build an average of tourist frequentation. So it really depends on your application and what message or what analysis you're trying to have. So every time we have a project, a study that you're coming to, the first things to do is to analyze and to understand the phenomenon that we are trying to investigate. It's physical temporality, presence, the other connection with the other environment, etc. Does that answer your question, Sonia? Great, thank you. Other question on optical data? Okay, so let's move to radar. So as I was saying, if optical data were easy to interpret because it was really looking like something we are used to see and used to analyze, radar data is different. So first, radar, what that is. First, it's an acronym. It means for radio detecting and ranging. And what does that mean? It means that it's an active sensor. If optical data was just passing over, taking pictures, this one is sending a message on the Earth's surface. It's sending and receiving a radio wave, and that is the signal that we're going to analyze. The difference between what we know we send and what we receive, what we call an echo. So we're sending what we call a pulse. So it's not a continuous. You can see I'm sending pulse, then pause, then pulse, then pause. And then I'm collecting the echo that are coming back from the Earth's surface. So of course I can collect all the echoes, because I can have, when a wave is reaching a surface, the reflection can go in many, many different directions. So I'm just collecting a little sample of the signal I sent, and that's what I need to analyze. The radar signal is also different. So before we were in visible and infrared data, okay? So this is the visible domain, the little where we were working with optical data. With radar, we're still on the electromagnetic spectrum, but way, way bigger wavelengths. If before we were talking in nanometers, the signal we're sending is now up to centimeters. So what does that mean? I have my satellite sending a wave, and this is the wavelength of my radar data. So we could say that this was an optical signal, and for radar, I'm actually expanding it. So I have a longer distance between my amplitude peak. In radar data, we have different wavelengths, X, C, L, and P band. So you see, we're talking again about band, because on C band, I'm just collecting information from the C band, not all the others. We are still having one image, one specific portion of the spectrum. So what does that mean? The distance of our wavelengths, the length of between the two peaks, is bringing actually information about what we call the spatial accuracy. So here is some example in the X band. So we have a radar image, and when I zoom, you can see the level of details we can have. If you remember, X band is the smallest one. If we compare to the others, so we have L band, so the longest, we can't see a lot of details. We can barely recognize housing here. C band, the one from the Sentinel-1 Copernicus mission, the one from ESA, we are using C band. It's a nice average, it's a nice conversation. And the X band, the one that are the most accurate, the smallest wavelength that allow us to see detail. So what does that mean? What is the connection between the wavelengths and the spatial resolution? When my satellite is sending a signal, it reaches the Earth, and then I have a lot of echoes. Depending on the surface it's reaching, I have different echoes. Here, on a very rough terrain, I have so many little features that it reached that I have echoes, and then the echoes are reaching another tree, and so I have a very disruptive signal. When I'm reaching a flat surface like water, I have a specular reflection. I don't have any signal back usually. It's really following the perfect Snell-Descartes law here. And when I'm reaching building, as you can see, I have usually double echoes. So if we take the example of trees, for example, on X band, I have very narrow information. The wavelengths are really close to each other because I have a very small wavelength. So I'm not going to be able to reach a lot into the trees, for example. At the first, it's going to directly bounce back on the first leaves at the top of the canopy. On the C-band, a bit wider, I have more space. The wavelength is a bit bigger, so I can actually reach more information and go a bit deeper in the forest, etc., etc. With the P-band, I didn't show you because it was too big. It's 65 centimeters. I'm even able to go through the forest canopy, reach the ground, and receive some echoes. All right, so the satellite wavelengths is giving me the spatial resolution. Any question here? Okay, so now we're going to go to another properties of the SAR signal, because we're sending a radio signal. So a radio signal has what we call a polarization. What a polarization means. So when I have my satellite sending a wave, I don't know if you can see, I'm sending a wave, a pulse. So let's imagine that this is just a pulse. I can be in a vertical polarization. So here you can see I'm in a 3D domain, and my wave is vertical. Another possibility is to have a horizontal wave. Actually, Sentinel-1 data is able to transmit a wave either horizontally or vertically, and is able to collect the information in horizontal and vertical. So we have a different combination of polarization, HH, VV, HV, VH. So here, HV, I transmit my wave horizontally, and I receive the echo, the vertical component of my echo. Why do we need this information? What is the point of having different polarization? Well, the way the wave reaching the ground is depending on what you see. I see we have a question. Have you used SAR for benthic habitat mapping? Aha! No, I haven't used SAR on the benthic habitat mapping because we saw that every time a SAR wave is reaching the water, I don't have any signal back. Actually, I'm just going to pass to the next slide. When I have a coastal area, I cannot see anything except the ridges. As you said in your message, we could imagine using SAR data at low tide, trying to monitor the habitat there. Yes, we could. But the SAR data resolution, spatial resolution, doesn't allow us to reach that very narrow coastal area. It's too small to be actually visible on SAR data. We're going to need, if we want to use SAR data to monitor low tide benthic habitats, we're going to need to use what we call commercial SAR data. We have SAR data that are really with a high accuracy, high spatial resolution, up to a centimeter, but those data are really expensive. And most of the SAR high accuracy data are usually for the military application. And you're going to see through the slide of the SAR data, other limitation make it really complicated to be used in coastal habitats. SAR data has been made and essentially made for interferometry and to monitor very small elevation changes over large area and long period of time. So monitoring detail on Earth, that is not the core mission of SAR data. That's not why SAR was made. Thank you, Ariel, for your question. I'm continue then with the polarization. So here I have the same scene that I reach in horizontal polarization, but I ask my satellite, show me the picture with the echo on H and the echo on V. And you can see that we cannot see the same features because horizontal and vertical polarization signal doesn't bounce back the same way over the same features. The example with the ref C, for example. With so this image is exactly the same. It's the same date, it's the same area. The only thing that is different is the return signal. Here, I mean horizontal, nothing at all. When I ask for the vertical polarization, I can detect the rough sea condition, the little waves, etc. The vertical polarization is used to detect objects with an elevation. Okay, because the vertical waves is reaching vertical features, and this is where then I have more echoes that are bounced back to my satellite, and then I can reach more information. So satellites, so the polarization is giving me the feature recognition. We cannot really talk about the spatial accuracy or the spectral accuracy here because we have just one spectrum. But the polarization, the type of polarization, allow me to make the difference between different features. Then we say that SAR is an active acquisition. What are the consequences? So SAR is beaming over the Earth and receiving signal. It means that when we optical data, we were dependent on the sun. Here with SAR data, we can have day and night acquisition. There is no more constraint about the sun reflectances. I can I can acquire a data at any time I want. Another really practical feature for the military acquisition. That allows us actually to have a very high coverage for SAR data. In some latitude, we are up to 2 days, even lower than a day at a frequency revisit. Another consequences of the active SAR data, it means that we can also go through the clouds because I'm sending a beams. We saw that the size of my wavelengths depend and rely on the features that are going to bounce back. But what is the cloud? A cloud is very dispersed water particles. So my signal can actually go through it. So here, I should have put them on the same slide, sorry. But I'm here over the Wash in UK, very cloudy area, very cloudy latitude. A picture, and at the same day, I have my SAR data. You see, no cloud at all. I can't even imagine that there was a cloud here. No consequences at all. So the fact that I have an active sensor increases my temporal resolution because I have no limitation of cloud and no limitation with the sun rotation. So we have some similar features than we saw with the optical data. We saw that we have wavelengths that giving me spatial resolution. We have polarization that could be linked with the spectral resolution because it helped me identify different type of features. And the SAR active acquisition is actually having an impact on the temporal resolution. Before I go to the SAR limitation, do you have any question on the SAR satellite acquisition mode? All right. Yeah, Arturo, question. Can the SAR satellites all mode at the same time? Okay. So you have some SAR satellites that are constrained to just one mode. You have some satellites that will just do horizontal and other that will just do vertical. But when you say at the same time, what do you mean at the same time? I can't at the same time send and receive. You see what I mean? It's temporal. So I'm going to send a wave horizontally, and then the post-treatment will just capture and put aside the vertical component and the other, the horizontal component. Then you say, can we reproduce synthetic polarization we need? So the polarization we need, no, because the polarization is linked with how the feature on the ground reflect and bounce back the signal. So if you try to recreate, because for example, you want to monitor wave ridges on the coastal area, and unfortunately, you don't have access to Sentinel-1, which is not possible. But imagine you don't have access to Sentinel-1. You only have access to a horizontal satellite that is sending and receiving in horizontal. So you could not predict or you could not modify that signal to make it vertical, because you're missing the core information here is what is the type of feature the satellite signal is bouncing back. Not knowing that, you cannot predict how the signal will look like. See what I mean? Does it bring a bit clarity, Arturo, on the polarization? Okay, great. For the ascending and descending mode, we're just going to go through that now, because actually that is, I put that in the limitation of the SAR satellites, because that bring actually to make the echo with Ariel question. It's really, really impacting what you can see and how you can see features. So this ascending and descending mode are just coming up. But first, we're going to start with the SAR signal complexity. We saw that optical data were really easy to understand and to interpret. Here, SAR data by essence is just a grayscale of data, but you can represent, for example, in this image, I have in blue, I have the HH, in green, in the green component, I have VV, and on the red, the red, I have HV. What does that mean? Those colors here have no physical understanding. Here, I'm on a desert. I think it's a Namib desert. I mean, there is no sense of it. The different colors are to be linked with different rigorosity on the ground. So the SAR complexity signal, the fact that a color is not because it's green. Hello? Okay. So the fact that you see something in green doesn't mean that you have a tree or a forest. You have to understand what signal you put in the green band to be represented as green. So the SAR complexity signal. Another part of the SAR complexity signal is that when you zoom, your pixel as it is visually has absolutely no meaning. To understand this, what you're looking at and the physical sense of what you're seeing, you need to know the polarization, you need to know the wavelengths, you need to know all the different parameters before you can even start trying to analyze the picture. I know. A lot of scientists are actually using SAR data, make a visualization. They're using GRV mode from Sentinel-1 with a polarization that allows them to make the difference between land and sea, and they're happy. They have a visualization data. But it's a visualization. You're not going to be able to monitor, for example, the health of the forest. SAR data is often used to soil moisture. But that only works if you know which polarization to use, which wavelengths, and what are the expected signal you're going to get. It's going to be a comparison to a benchmark. So SAR data bring a lot of information. When optical data was just reflectance, SAR signal is bringing you frequency and polarization. But you need to understand, and you need to be able to combine this information to get a scientific information that you can use on your study. Another complexity, another limitation of the SAR signal is the noise. So we know the SAR is sending a beam and collecting the receiving. If I take the example of a boat in the middle of the ocean, a boat is going to be a flat surface, white. I want to have a very high reflectance, a lot of echoes are going to be bouncing back. And the problems, I have so many signals, so many echoes that are coming from that boat that when it reaches my satellite, it's going to infect the other cells around it because the signal is too strong. And when you look at so it's really practical to detect boats, no problem there. But the problem of this is that the signal is so intense that it's gonna mask out other information. So here it's practical, we don't care because it's the water anyway. There is nothing below the signal. But let's imagine that type of signal in a city. You have very high building with a lot of specular reflectance. It's going to mask out other pixel information. So SAR signal can be really noisy. And I'm passing because I want to keep it simple. I'm passing the thermal noise, I'm passing the speckle noise, because all those, even there are limitations, we have processes that can be really helpful to reduce and to correct them. So it's a limitation, but we can manage with it. Another limitation, and here we're going to have Arturo question, is the SAR signal geometry. So what does that mean? SAR data, if I take optical data first, here, optical data is acquiring picture at nadir. We call it nadir. It's a vertical acquisition. So I have exactly the same distance between the center of my signal to the edge. SAR data? No. Why make it simple when you can make it complicated? SAR data is a right side looking acquisition. So imagine your satellite. I don't know if you can see me on the picture on my video, but you're the satellite, and instead of just looking down, you're looking right. And this is how you're going to acquire your data. So right side looking. What does that mean? Mean that it's right, acquiring data looking at the right. But the satellite is orbiting around the Earth. So sometimes we have an ascending path and sometimes a descending path. And according to ascending or descending, I'm not going to have the same vision if I'm going up or if I'm going down, because I'm always looking at the right and I'm going to be able to see the same picture. Here I took the example of an artificial coast that I created. Here my SAR signal is going to bounce back to the cliff and just going to be able to see the beach. When I'm going up in ascending path, I'm going to be able to see, for example, the cliff edge and the rocks building the cliff. So my acquisition, ascending or descending, actually has a huge impact on how I'm going to see the picture and the features that I'm going to be able to see in my on my picture. Okay, and it means also that a picture, when we saw, for example, before Sentinel-2A, Sentinel-2B, there is absolutely no difference between the picture. A picture in SAR ascending and SAR descending are really, really different, and you have a high geometry and topography distortion. Let's do a bit of geometry. So I have my SAR signal. Here it's my near range. So these are the boundary of my SAR width. The near range, my satellite is here, and the force north near. I have a cliff, a little mountain. That is, no, my far range is here, sorry. That's the plane, sorry. Far range, near range. I have a cliff there, and this is the image that's going to be recreated based on what I see on the ground. So as you can see, because my satellite is taking the picture, I have to represent the feature of sea on the mountain on my plane of my image. Even if you can see here, the blue and the red crest, mountain crest, are the same distance on my image because of my geometry acquisition, because of my right side looking acquisition, I'm not going to have the same distance. The crest near to the closest to the near range is going to be way more smaller than the one from the far edge. And that's because when we saw, for example, on satellite data, pixels were square. Here, my pixels are not square. The farthest I am to the nadir, the longest is my pixel. So we have a difference in distance and a difference in geometry. But another thing is that the same problem that we saw with the cliff, I have shadows area. I have my satellites. It's reaching the mountain, and I have the signal reaching the peak. And any signal going after that, I'm not going to be able to see that face of the mountain because of the peak. So I have a shadow area that's masking all information that could be here, but also on the near range of the mountain. So, of course, because you have ascending and descending, it means that the next time my satellite is going to be over there and I'm going to be able to see this face. So, yes, if you do a whole cycle, you're going to have a complete image. And this is one of the processes that scientists are using to correct the right side looking image to a nadir image by combining ascending and descending. But it means that between ascending and descending, nothing had changed. Here we're looking at mountains. So yes, we can presume that during the 3 days of ascending and descending path, nothing had changed. But if you are actually monitoring element, more dynamics element, well, you can't be sure that between your ascending and your descending, you're still looking at the same objects. If we are looking at consequences, real life consequences of this ascending and descending, here we are in Barcelona. So we have a very nice stadium in optical data. You see nadir optical data. I'm really above it. When you're looking at inside data, well, you have the projection here of the seats. You can see the shadow there of the stadium. And you're masking a lot of information. Here we should have a parking lot. I could not see the parking lot. Here we should have some buildings, very difficult to see because here I have the echoes of my stadium. Another one is this very tall and very famous building in Barcelona. When I'm going with my satellite is making an acquisition in ascending, sorry, right side looking. My building is actually having an echo that is covering the whole roundabout. Here is a roundabout. We have streets, cars, major access. I could not see that because of the echo of the tower. Arturo, is it a bit more clear about ascending and descending, or do you have a follow-up question? Okay, I will. Well, don't hesitate if you have a follow-up question on ascending and descending path. So back to limitation. So we had the limitation of the geometry because of we not acquire the data at nadir, but ascending and descending because we are right side looking. Another problem of this geometry is that it impacts the spatial resolution. I give you a little preview when I said that the pixel size on optical data, because of we are nadir, is perfect square. It's not the case with our star data. We saw here I have my star trajectory and my acquisition right side looking. So you can see that my SWAT, the area where my satellite data is acquiring data, is not the same. It doesn't have the same side. It's exactly the same principle why we have climate on Earth. We have a signal here, the same beams here is covering a larger area than is actually covering here. So at the near range, I have a higher spatial resolution than at the far range. Some data, and you can have access to Sentinel-1. I'm not going to call it raw data, but before the transformation, you can actually see and have access to those non-rectangular and non-corrected pixel size, because if you go to the level 2 sound data, it's all being corrected and you have a pixel of 10 meters. But so I have my information, and if the information here in yellow, it's my pulse, it's reaching the ground, it should reach the ground with the same intensity, but it's covering a larger area. So I have the signal that is more diffuse, and the echo will have less intensity. So the geometrical acquisition of SAR data also have an impact on the spatial resolution of the data I'm gonna have, because I'm not gonna have the same intensity of signal that reach the ground, and then of course my echoes, the pulse that reach back from the Earth, will not have the same intensity. So that's what we call the border noise on the satellite data. Usually we just cut it down. We disregard when we are too far from the edge. There is some SAR data now that are actually proposing a more nadir acquisition. But the problem that we have with a nadir acquisition is then the wavelength. The antenna that actually send and receive the signal is not adapted, and we have problem with the wavelengths. To finish with this presentation, before I give you the floor for the questions, I have 2 more slides that present just different type of satellites. So keeping with our radar data, here it's SWOT. SWOT means surface water ocean topography. And what SWOT is doing is actually you have 2 antennas that are taking the picture at the same time. So you have ascending and descending acquisition at the same time, and that allows you to recreate topography. So you can recreate elevation. You can follow the seawater, the water surface elevation. Really useful, for example, to monitor sea level rise. So you have also Sentinel-3 from the Copernicus mission that is doing altimeter data, but not with these 2 antenna system. It's a more double pulse and an echo sounding. Another type of satellites is LiDAR. So we saw optical, we saw radar. This one, LiDAR data, is laser. We send laser beam. It's usually really used, and I know Namria is using it a lot when they're doing the bathymetry echo sounding. This is exactly the same system. We're sending a laser beam to collect information. Right now, the laser that we have and that we're using, especially in the Copernicus missions, mostly focus on atmospheric data retrieval, because once we can reach the Earth, we can, but the atmospheric layer brings so many noise and is so disruptive to the LiDAR data that we can receive that the information we have is really, really coarse, a lot of inaccuracy. So there's still improvement to do for LiDAR data for Earth observation, but really useful LiDAR data, really useful for atmospheric monitoring, weather forecasts. Most of meteorological offices are using LiDAR data. That's all for me for today. Do you have any question on what we saw? We can go back to optical if you didn't have the opportunity to have your question, or if you remember something. Comparison radar, optical, or specifically on radar limitation on radar data. Do you have any question? No question? Okay, brilliant. So a little preview for tomorrow. So we saw here all the information about the satellite we can use for Earth observation. But now, how exactly it's going to impact the analysis we're doing? We had a very interesting question on the use of sound data for low tide monitoring. That is, we're going to see tomorrow the impact of sound data on benthic monitoring. We had the question about the decision between temporal resolution and spatial resolution. Tomorrow, I'm going to show you real example of real project to show how this trade-off has been decided and how we made the decision. And of course, also with the ascending and descending, I will show you the consequences that it had on coastal monitoring when we tried to use sound data to monitor the land-sea boundary in coastal areas. So I'm really happy for today. Thank you very much for all your questions. And if you want to see the application of all this theory, see you tomorrow.
We're happy to once again be joined by our speaker, Anne-Laure Beck from Argans, and she'll continue walking us through the practical case studies and help us connect the theory to the application for benthic habitat monitoring and management. So Anne-Laure, please.
Thank you, Carla. Hello, everyone. Really happy to be with you again today. As just Carla said, so yesterday we saw the different type of satellites, the most used for Earth observation, and the one that we can be that can be applied to coastal and benthic habitat monitoring. But it was really, really theoretical. I know sometimes it's difficult to link a theoretical concept with a practical example. And the question we had yesterday were essentially regarding how we can apply, how we can decide based on the application, for example, the trade-off between spatial resolution, temporal resolution. So all those we're going to try to see today. Before we dive in, is there any follow-up question from yesterday? After today, you probably think about it, and I don't know if there is any question before we start on the principle. Don't hesitate. Again, raise your hand or type, and I will respond as we go. Otherwise, we can start. For today, the application example part, it will be smaller than yesterday. We're really going to focus on two examples. Examples that are coming from ESA project, ESA funded projects, one ongoing and one that is actually on these final stages. So yesterday we saw that optical and radar satellites have, even if the signal are really, really different, we saw that was, hello. No. We saw that the some elements are common to both. For example, the temporal resolution. So how many days I have between two acquisition of the same area. The second one was the spatial resolution, the size of the features I can see on the ground. And the other one was the type of feature we can see thanks to the spectral resolution. So spectral resolution was really linked with optical data because we saw that with radar, it was more linked with the type of polarization that we can have. So I will propose you to start with an example of coastal monitoring. So coastal monitoring is really essential. You know that with the rising of the sea level, with global warming, we have more intensive storm, we have subsidence, and the coast are really that are usually stable, are getting either erosion or accretion. It's important to note right away that there is always erosion, even when global warming was really small, we always had coastal erosion because coasts are dynamics. And every time we had erosion somewhere, the sand was accumulated on the other one. And usually it's seasonal cycle. What is eroded during the winter, it's coming back during the summertime. But what's new is that with the changes in the environment, we see some chronic erosion. We change the balance of the sediment cell, and the world is resilient. So it's trying to readapt and to find an equilibrium, but that means that it's changing the shape of our coast. And because a lot of population are living in coastal areas, it's really important for us to monitor it. So what we aim to identify with this case study is that a time series to identify where erosion hotspots are, and more important, why we have erosion in this place. Because you cannot solve a problem if you don't know what the problem is. And erosion is not a problem, it's a phenomenon. You need to understand first and foremost why you have erosion there and why there was not erosion before, what changed in your system that lead to that new equilibrium. So for that, time series. And time series of what? You have different indicators, and study are bringing a lot of different indicators. The one that is really common and the really easy to use and make more sense is the delimitation between the wet sand and the water. I'm not talking about wet and dry or vegetation line. No, what I'm trying to identify, if I show you on the slide, is really after the wave breaking. But here I have an issue because satellite data, we saw I have a lot of information. I can bring a lot of, extrapolate a lot of indicators. I can use the spectral bands to build a lot of different indicators. And here what I have, it's not the land and sea boundary. No, it's a wet and dry sand boundary. And if sometimes I'm actually extrapolating or extracting that instead of the line I'm wanting, well, I'm not looking and comparing same results. So even if coastal erosion, coastal monitoring is a real challenge for today's stakeholders, the study, what we had before, it's lacking some consistency and some accuracy. So ESA decided to bring together a lot of different actors in the Coastal Change from Space project. And during this project, what we wanted to do is having an indicator, land-sea boundary, always the same, always extracted, to be able to then build time series of the coastal area. So for this case study, what satellite can we use? So here we're going to see the difference between SAR data and optical data for this problem specifically. So we had, for the one that was here yesterday, you remember this picture of a VH and a VV polarization image from SAR. It's the same area, it's the same date. Wait. Hello? All good? Okay. The only thing is different, so it's the polarization. From this picture, I would like to extrapolate, to extract the land-sea boundary. The problem with SAR here is I don't know what I'm extracting. We don't, and this is an easy case because I'm having an east-west coast. If you remember when we were looking at the geometry yesterday, if I had a north-south coast, the problem is with the right side looking acquisition mode, I will have shadowing, I will have effect of distortion, and I will never know what I'm extracting. The fact is, we can imagine here, we can all see here on the SAR data, a boundary there. But this boundary, what is it? Is it wet, dry sand? Is it vegetation line? Is it land-sea boundary? We don't know. Same here. And actually, if you look, if you compare, the line I have here is not at the same place as the one I have here. But we know that it's the same date. So the indicators should be at the same place. So the problem with SAR is the lack of consistency. Here with the time series and due to the change on the roughness of the sea, I will not be sure of the consistency of the line I'm extracting. Maybe sometimes I'm going to have the land-sea boundary. I also take the risk that sometimes I will not have it. If I take optical data, I can see the different boundary that I have. I can make the difference between the dry sand, the wet sands, and the sea. So that's why for this project, for the coastal monitoring project, we decided to go with optical data. We use also SAR data because we saw SAR data had a really interesting temporal resolution. But what we lack in spatial accuracy with SAR data, we can trade off with the temporal accuracy. But the calculation of your error bars here are really important because you have to take that into account. Now, I'm just going to focus on optical data and see, for example, the impact of the different type of resolution. So first, the spectral resolution. We saw that optical data are acquired through different bands. And these bands are really specific. They're really narrow, and I have then the reflectance information corresponding to the band. So I have access to a lot of different indicators. So I want to identify here the difference between the land and the sea. So I will try to use different band information to combine them differently. And looking at the different threshold I can have, I can always identify here, here, and here, a gap, a significant gap that is matching the transformation of land pixel into sea pixels. Now it's just which threshold in this situation is the most visible, the biggest. So here with BNDVI, in that situation, we can see that the trade-off is significant and it will be easier for the algorithm to extract then the appropriate boundary. It's important to say here that BNDVI, in this case, is the most accurate, it is the most representative. But depending on the type of coast that you have, sometimes you need to change the index. For example, in volcanic area, you might have a darker sand. Well, with darker sand, NDVI will be more interested. If you have a coast that is directly a cliff, or if you have a coast that instead of sand, you have vegetation, then you need to adapt your spectral index. So always adapting the spectral information you have from the spectral resolution to the situation. And here with Sentinel-2, with the 30th band we seen yesterday, I have enough information to extract. In most of the cases, we managed to extract it for 99% of the coast that we had under our in our study, the accurate line. We had some issue when we were working in the Canadian area, where we had a really flat area with very dark murky water, with mud beach and wetland. That was a bit challenging, but still, in all of the cases, we managed to extract accurately the line. Then the impact of the temporal resolution. So again, and as we said yesterday with the question that we had on that topic, the selection of the temporal resolution is definitely rely on what you're trying to identify. Are you trying to monitor and to identify beach rotation, or the sea level rise component, or the beach state or the storm erosion? So the selection of the event that you are trying to identify and to monitor or to map, you will be able to select the temporal resolution that you want. So sometimes yearly data are enough, depending on what you're trying to identify. But if you're trying to identify, for example, and to monitor or to map the impact of a storm on a beach, and you're trying to work with seasonal data, so let's say, for example, an image every 2 months, well, you're never going to be able to map the impact of your storm. So the first question that you have is what I'm trying to do. What do I want to represent? So in this project, because we had sand transport, we have wave impact, we wanted also to do beach rotation, storm, we decided to go with the smallest temporal resolution possible, 1 image every 5 days. We use every single image available for the area. It was a huge data set. But it allows us to build some analysis like this one. So we were discussing the impact of storm. Here, with the different shoreline that we made, so it's mean sea level shoreline. With the different shoreline that we've made, we managed to analyze and to identify, for example, different movements. So the first one was the beach renourishment in May 2015. We moved the mean sea level shoreline onwards. But very, very soon after that, in November 2015, a huge storm arrived. I think it was the Gloria storm. And it totally reduced and corrected all those beach renourishment that we had. And then second storm in January 2016. So you see that if I'm using 1 image per year, for example, or an average of lines or an average of image, I will never be able to identify and to map those changes because they're too close in time. The fact that we have one date, one line, this allows us to identify and to monitor and to follow all the little events that could be interested. So here it was for Barcelona. Another example is the beach rotation. So I told you at the beginning that erosion is a dynamic phenomenon. And it happens, and sometimes during the winter, what you erode come back during the summer. This is the perfect example. So here we have pocket beaches. They call pocket beach because they build protection along the coast, and that created single sediment cells that they call pocket beach in Spain. And we can see that during the summer to the winter, we have an erosion up north. And during the winter time, we actually are having a rotation of our beach. And when we link it with the waves, with the sediment transport, we can see that we have a shift between summer and winter time of the trade-off of the current. So due to the different seasonal change, we were able to identify the different beach rotation. And if we were using, for example, I don't know, annual data, I'm probably just going to see erosion and not this rotation. And the problem is I see erosion, so I want to correct the erosion. I'm going to block the onward sediment transport that is coming during the summertime. And then I disrupt my system, and the beach rotation is not happening, and it's just eroding because it needs to readapt. So that's why the selection of the satellite mission you use for the different thematics is really important. Before we go to the next example, that will be more linked with the CopPhil project, do you have any questions first on that example on coastal monitoring? Any question? Okay, so let's continue with the benthic monitoring example. So what are the objectives of this use case? So this is within the CopPhil initiative. What we are trying to do here with the benthic thematic is first to retrieve the depth in the Philippines. So here we have the example of Boracay Island. But also, we would like to retrieve the different habitats that you have to be able to follow them through time. So 2 really different objectives, 2 different maps, and so 2 different needs in terms of data and in terms of resolution. So again, what satellite data will we use? Well, the problem that we had with SAR is that it cannot go through water. So when it reaches water, depending on the type of waves or the type of element that you have on the surface, I will have different backscatter. So I can have specular backscatter, really nice, tidy, perfect Snell-Descartes properties. Or if I have rough water, I can have a backscatter that go in all direction. And so I will have different signal, but I will not go through the water. So SAR data to monitor, to retrieve depth in this situation, not really helpful. Optical data. Well, we have the problem that we know that to collect the data with optical sensors, we actually retrieving the sun reflection from the ground, from the Earth's surface. So it means that my ray of light, let's call it this, my ray of light is coming from the sun, going through the atmosphere. Then I'm on the Benthic monitoring, so it's reaching the water surface, then it's go through the water, reach the seabed, reflectance going up again through the water surface, through the atmosphere, and back to my satellite. You can imagine that it's a lot, and there is a lot of partition of data when we do that, when we go through all those different layers. So the use of optical data for Benthic monitoring, well, yes, we have that because we can't use SAR, but we have to be aware of all the information we're losing. More than that, when we go through the atmosphere, we don't lose a lot in terms of spectral resolution. But when I go through the water, the ray of light, the visible spectrum, and even infrared, more infrared than anything, is actually absorbed and could not reach the bottom, and all wavelengths are not going as deep as the others. For example, the red wavelengths are directly absorbed. So the first meters, up to 5 meters, no red afterwards. No red. That's why we call it the deep blue, because the blue is the only wavelength that can go deep and not be totally absorbed in the first meters. So here, the use of satellite data is really important. So why coastal water is not going as deep as open water? That is mostly due to the different particles that we have in coastal waters. You have a lot of suspended matters in the water column that is increasing the absorption of the optical signal. So this is the result that we have, SAR data and optical data. So you can see that with SAR data, I cannot reach at all the different elements around the island. I have the island, I have nice boundaries. We can see here, just to make the link with the previous use case, you can't even see the difference between the beach. Here you have some cliffs, so here we have some shadows because of the orientation. So it was just to show you the orientation and the selection with SAR data. But when we talk back to Benthic monitoring, I cannot access shallow water information. With optical data, it's not ideal. You can see that it's way more clearer on land than below water, but still I can see some features. We can recognize some elements. Here we have some sands. Here it looks like we have some rocks. Here probably some seaweed. So at least I can see something with optical data. So for the Benthic monitoring for CopPhil, we only use optical data. Then the impact of the spectral resolution. So the idea to retrieve depth, to build a bathymetric map with the send-to-coral process that we are using and developing within CopPhil, is to collect information in different bands and using a benchmark. It means that you have some data that actually Namria was really keen to share with us. And with those data, in situ data, really accurate data, we can then match an information in terms of reflectance intensity with a depth. But now, which band I'm going to use? We saw that different information, the wavelengths, are not reaching the bottom of the seabed together. There is different type of absorption. There is a discontinuity absorption. It's not the same for all. So band blue of Sentinel, band 2 of Sentinel 2, that's blue, 3 is green, and 2, this is 2, sorry, mistake. Oops. This is 2, this is green, and band 3 is red. So you can see that in the blue band, it is actually matching the graph we have here. I can access a lot of different features. I can see different morphology. I can see different texture. I can see more deep, actually, even than with the green band. With the green band, it's a bit reduced. I have access to other type of features, other type of texture, but I have less information in the higher depth. In the red wavelengths, nothing at all, except maybe some shallow sand and some tidal area here, but I can't see anything. So the spectral resolution here is really important because I need spectral bands that can access the seabed. For the benthic habitat monitoring, the spectral resolution is really important, but not as essential as for the bathymetry retrieval. So here we have some nice pictures of monitoring sites around the Philippines with different type of environment. We are already below the water. We don't have to cross the atmosphere. We don't have to cross the water surface. We already below water. And even on this picture, you can see there are these different areas, different sites. The difference in colors, even by eyes, the identification of the different, for example, coral species or algae species is quite difficult. So the spectral resolution for the identification of benthic habitats is essential. It's really important because we have so less information. The information we can access to differentiate the different type of habitat, it's so reduced that any band needs to be used. We need to use as many data as possible, as many bands as possible, because in this situation, even little information is really useful. So for the benthic monitoring, either for the bathymetry retrieval or for the benthic habitat identification and then monitoring, spectral resolution here is key. We need a lot of spectral bands, especially in the blue side for the depth retrieval, because those are the bands that reach greater depth. But we also need a lot of different bands through the whole spectrum to be able to identify and access the differences, the spectral reflectances of the different habitat type. Then temporal resolution. So the temporal resolution for the depth retrieval here, well, it's not every day that you have your bathymetry that change. The bathymetry is seabed morphology is quite stable. You really need a very huge storm to disrupt everything and to move everything around. So with the bathymetry retrieval, one satellite image is producing one bathymetry map. So we don't have this temporality, this seasonality, because the depth doesn't change in season. So the temporal resolution here for the bathymetry retrieval, not really relevant, except that you just need to collect the data when you can and when you have cloud-free data. The temporal resolution for the benthic habitat monitoring, that's something else. We saw that even with a lot of spectral bands and or even when our nose is on those different habitats, it's difficult to make the difference between them just by difference in colors. What we can use is then difference in colors in time. Benthic habitat, just like habitat on land, are changing with the season. They're changing, they're adapting, there is seasonal cycle, there is development cycle, there is growth. And here, we can see that the different habitats doesn't have the same cycles. They don't change the same way with the same frequency and at the same rate. It's like if I take another example, for example, on crops. If I'm looking at a crops picture in June, all the crops will look the same. But if I compare those crops with another image, let's say in April, they're not going to be at the same stage. They're not going to look the same because they are different type. And then by combining the two information, the one in June and the one in April, I can make the difference between the type of crops. Here is the same idea, less obvious, of course, because the changes are smaller and the changes in reflectances are also more difficult to identify. But if we combine the information from the different spectral bands with the information from the temporal cycle and the temporal evolution of the natural habitats, then we will going to be able to manage and to identify different type of habitats. So here it's a time series that we use for the Benthic Habitat Monitoring through 2023. So I know the changes are not that obvious by eyes when we look at those pictures, but there is changes. There is changes. And the process that we are using for the Benthic Habitat Monitoring is able to detect those changes. That's why actually machine learning and deep learning techniques are really useful in this kind of situation. We usually went to periods of time where satellite data were only used to support visual analysis. Our eyes were the most powerful tool that we had, and changes that we were able to see visually were true changes. Now we have enough data, enough knowledge, enough experiences with those data to know that sometimes algorithm, computer science can see patterns where our eyes cannot see. Really useful, for example, for medical imagery, but also in Earth observation. So those little changes that for us, if we look at this time series, are more linked with different in water level, difference because of the illumination, changes because of the cloud presence. All that is been harmonized in the classification process that we use for the Benthic Habitat Monitoring, to ensure that the change we see and the change the algorithm we work on are only change in seabed environment. And then it's going to learn from those changes and being able to make differences between the different type of habitats. But that's going to be for next time. All the evolution of the different algorithms that we can use, the different machine learning and deep learning techniques that can be used for benthic habitat monitoring and also for bathymetry retrieval. That will be the practical exercise that we'll do, I think, in May. Thank you very much. So as I told you, way shorter than yesterday. So any question on this application? Is it maybe clearer? Did it help you understanding and contextualize the theory that we saw yesterday? No question? Right. Okay, well, if no question, well, thank you very much for being with me today. And so the next training for Copernicus will be in May, I think, beginning of May, to have the different applications. So we saw the theory yesterday. We saw some application example today with the focus on the CopPhil use cases. And next time, you're going to be able to test this process that I show you today and see firsthand how it's going to, for example, if you add a date, how it's going to impact your result. If you reduce the number of bands, how it's going to impact your result. So next time is really practical exercise that you're going to be able to test. Thank you very much.
Okay, so just a little bit before we close the session. So again, thanks, Anne-Laure, for the comprehensive benthic habitat monitoring discussion. We'd like to share now the regarding the materials. So here, I'm presenting the CopPhil Digital Campus, where you can find the training material. So for everyone, we encourage you to register and create an account to also access all our training sessions from before. So we had the introduction and then the land cover, forest, crowd motion. And now we will be launching our course page for the Benthic Habitat Monitoring Fundamentals. So here we already have some descriptions, and then the slides are already here made available, and you can download the slides of Anne from here. And then the video recording will be uploaded soon. And also some extended materials will put some relevant sources here. And what's important for you also would be the certificate of attendance. So you would be eligible for this certificate by answering two forms. So one is a training feedback and the other one is a short quiz. So all this on the platform, and yeah, to follow for the other courses, we'll reach out to you again and invite you for the next one. So yeah, so stay tuned. And again, thanks for everyone. If you have questions, you can send us an email also on the courses. By the way, you can also try to start some discussions. We have the discussion board in here. And yeah, so just reach out to us, and also we'll reach out to you for the next training session. So watch out for May and then maybe July and August. So again, thank you everyone. And yeah, all good, and have a nice day. Thank you.
Thank you.